the second fundamental theorem of calculus, which is, it says here example 1, but if you notice the notes, there is only one example, so it is the example. And in this example we have a function called a of x, which is the integral of this function f of t with a low bound of 1 and an upper bound of x. So we're going to let the upper bound vary, that's our variable, and we're going to watch how the integral either increases or decreases. So over here, this is our function f of t. So make a note here that this here is f of t, and then we're looking for a of x is the integral. So let's do this. I'm going to have you skip all the way down to part E here, which is no longer optional, because I've just crossed out those words optional. And what I'd like you to do is I'd like you to fill in this table, and I'm going to even, make this 0, and I'll start you out here, and then I'm going to have you pause the video, fill in the table, and then come back to this and make sure that you're understanding exactly what this function a is doing. Right? So the function a, when x is 1, right? So we'll go back up and look at this. The function a when x is 1. So what that means is if x is 1, we're going from the lower bound of 1 to the upper bound of 1. And we're essentially looking for the integral of that line segment right there, which is 0. Right? So if you go from 1 to 1, there is no area, right? So the first value down here, or not the first value, but the value when x is 1 is going to be 0. So again, pause the video, do fill in this table, and then come back and see whether or not you've Alright, so how'd you do? Alright, so just quickly, just to make sure that everybody's understanding this concept here, if when x is 0, we're going from 1 back to 0, so then the area is these 4 squares, so a of 0 is going to be negative 4. When we're going from 1 to 1, we already did that one, a of 1 is going to be 0. When we're going from a lower bound of 1 to an upper bound of 2, it's these 4 squares, which is why a of 2 is 4. A of 3 is going to be these 8 squares in here. Going from 1 to 4, we're adding on 1, 2, and then this is a third square. So a of 4 is going to be 3 more than we had previously, which gets us to 11. And you can see how we can kind of march our way across. When we get in here, we're subtracting 1 from the total area. Here we're subtracting 3 from our accumulated area. Here we're subtracting another 3 from our accumulated area. Here we're subtracting 1, and then we add on 1 from our accumulated area. Right? Now the other thing to note here, and there's actually a nice little space here for us to note it, is that the derivative of this a function is the f function. Right? So we could up here label the y-axis. We already labeled it f of t. We could also label it as the derivative of the ax function. So this graph serves two purposes. All right, so now let's walk our way through these. A. So where is the function a of x going to be increasing? Well, the function a of x is going to be increasing wherever we're adding on area, right? So we start here at 1, and then from 1 to 5, and here we're always increasing, and actually going from 0 to 1 we are increasing. So this function is going to be increasing wherever x is less than 5. The other place that it's going to be increasing is this little piece right in here between 9 and 10. Actually, yeah, between 9 and 10. So we could say that where x is greater than 9, right? So there are two intervals where the function a is going to be increasing, and then that means that in between those, when x is less than 9 or x is greater than 5, then the function must be decreasing, right? When does the function have a relative maximum? Well, the function has a relative maximum when its derivative goes from being positive to negative, right? So again, this graph here is showing us the derivative of the a function, and the derivative in this range here is all positive. The derivative down here is negative. Right, so the derivative at 6 is going to be -2. The derivative at 7 is going to be -4. So right here at 5, we're going from being positive, having a derivative that's positive, to a derivative that is negative. So at 5, we have a relative max. Right? So this is when x is equal to 5. A relative min is when we go from having a derivative that's negative to a derivative that's positive, and that's going to happen down over here when x is equal to 9. That's when the derivative is changing from negative values, the values that are below the x-axis, to positive derivatives, the values that are above. Right? When is it going to attain its absolute maximum? Well, it's going to attain its absolute maximum either at 5 or at one of the endpoints. And the endpoints are 0 and 10, and so we can just compare. At 5, the value of a of x is 12. At the left endpoint, the value is -4. At 10, the value is 5. So it's going to obtain its maximum when x is equal to 5. And the maximum value we already filled in down here, so the maximum value is 12. Right? The absolute minimum is going to be either, come back here, so it's going to be either here at the relative minimum at 9, or it's going to be at one of the endpoints. And right, so we want to check, where is it at 9? At 9 it's 4. At the endpoint here it's 5, so 9 is less, the a of 9 is less than a of 10, but way over here at this endpoint, the first endpoint, the value of the function is -4. So the absolute minimum is going to be at 0, and it's going to have a value of -4. All right. Moving on. So f, the derivative at 4. Well, the derivative of 4 is, well, remember that this graph way up here, at 4 its derivative, right? So this is the derivative of the a function. At 4 its derivative is going to be 2. And the second derivative is going to be the slope of the derivative graph. So if you look up above at 4, then you can calculate the slope by just simply counting. You go from that line is going down 2 and over 1, so the slope at negative 4 is going to be negative 2. Right, and then we do the same thing at 9. So the value of the derivative graph above, right, the function a, its derivative, the value at 9 is 0. And then the second derivative is going to be the slope of the first derivative graph, and that graph up above is the first derivative graph. So the slope there is 2. At 7, I can actually just read it right off of, well actually no, sorry, we can't read it off the table. This table is giving us the values of a. We have to read it from the graph. And at 7 on the graph, we are all the way down here at negative 4. So this is negative 4. And then the derivative of the derivative graph, or the second derivative, we have a cusp. So at 7, we have an undefined second derivative. All right, last two questions. So when is the function concave up? Well, the function is concave up when, right, the a of x function is what we're talking about. The function is concave up when the second derivative is greater than 0. Now the second derivative is greater than 0 when the slope of the first derivative graph is greater than 0, and that happens, the slope of the derivative graph up above is greater than 0 when we have a positive slope, when it's sloping up to the right. So that means that when x is greater than 7 or less than 10, which is the right-hand side of our interval that we're interested in. And then the last one, the inflection points. Well, to get the inflection points, we have to figure out where the Dyer points are, right? So the Dyer points are when the second derivative is 0 or undefined, and the second derivative is 0 when x is... Alright, hold on. Let's make this clear. So we're looking for... I got myself confused here, so I'm going to go back and do this a little slower. So we're looking for when a of x has inflection points. So we're looking for when the concavity changes from concave up to concave down, or when the concavity switches. We're looking at Dyer points. So the Dyer points are when the second derivative is either 0 or undefined. So we have up here, right? So if this is the graph of the first derivative, we have tucked in here second derivative. All of these are when the second derivative is 0. So we can consider these to be all Dyer points, if you will. And if we're looking for an inflection point, we're looking for the inflection point where the concavity is changing, which would mean where the slope of the derivative graph is changing. So we don't have the slope of the derivative graph changing along here. This is where we start, and we're not going from concave up to concave down here, right? So we're going from no concavity to, and this here, because it's got a negative slope, this is concave down. The other Dyer point we have is here at 7, where we have our second derivative is undefined, and here the second derivative, the slope of the first derivative, the second derivative is going to be negative, and then here the second derivative is going to be positive, so we're switching concavity right there at 7. So 7 is a Dyer, 7 is a Dyer point, right? So our Dyer points are Just our points are when x is less than 3 and when x is equal to 7. None of those work for inflection points, and this is an inflection point. And we are done with the third set of second fundamental theorem of calculus notes. Ta-da!